Hey everyone. Again, uh, today we are going to start with the quantum computing part of this introductory course. So we are basically going to speak about the qubit. Um, and this is the things that we are going to be talking about today. As first, I will talk about the classical bit. After that, I will go to the quantum bit, that is the qubit, right? Uh, After that, I will discuss something about different types of qubits. I will describe a different way of representing qubits, and that is the Bloch sphere. And also, I will talk a little about density metrics, pure and mixed states. Um, uh, for the final part, we will discuss a little of multi-qubit systems, right? So let's go straight. So basically, for computing, everything we see in our phones, in our laptop, or whatever electronic device with a screen are zeros and ones. I guess you might have heard this before or not. I don't know, but you can encode anything you want in different combinations of zeros and ones. For example, I have here the binary some binary combinations, right? For numbers or letters or I don't know. I mean, you can encode anything using just zeros and ones, and that's what is called the binary code, and it's how computers work in the deep down, right? That is how they work deep down in the base of everything. So, how do we represent this zero and one state physically, right? Inside my laptop, for example, right now, or your computer or anything, any electronic device. How are these zero and one represented, right? So at this point, all the computers, electronic devices, and all that stuff are made out of chips that have a lot of transistors in them, right? So I know that for sure I'm not going to describe with details what is a transistor, but the only interesting thing for us is that the transistor can have like two states in the sense that one state is the when the transistor is off, and that means that it has a low voltage. We can call this low voltage state, we can call it zero, and also the high voltage state when the transistor is on, and we can call this other state the state one, right? So with that a lot of transistors in a chip, we can do different computations using electric signals, right? And that's how everything works. So, but in order to understand a little, because we're talking about the classical bit, right? Because uh, we are saying that the transistor can be in the state zero or in the state one. But in order to properly understand transistor, you have to go to quantum physics, right? And quantum mechanics, because the theory or the let's say the behavior of the transistor is classical because you have, at the end you have an equation, and the equation is like is the doesn't follow the rules of quantum mechanics. But in order to get the equation that tells you about the how a transistor works, you need to go very deep down to understand solid state physics, and it has to do with how materials, the properties of the materials, how do I mean, for example, electrons move in the material. In solid state physics, there is something called band theory, that is just how the electronic levels, let's say, are extract like the electrons. have some kind of an structure between the material. For example, this are, is a representation of these bands for some material. I don't remember what material exactly, but maybe silicon or other stuff. And also these representations are related to solid state physics and band theory. And when you understand everything that, and for that you need quantum mechanics, because in order to understand the movement of the electron and a lot of different things, you need to use the Schrodinger equation and some variations of the Schrodinger equation, use numerical methods and quite complicated things in order to properly understand materials and being able to take out the interesting properties that we use in computing. And after that, you apply this theory to semiconductors, and you get semiconductor theory, right? That is similar, but specialized for semiconductors that has a material that have certain properties. And when you study and understand semiconductor theory, at some point you get to what is a transistor, how does it work, and how can you make one. So the point of explaining this here is just to make you understand that the classical bit is something that exhibits classical behavior in the sense that, all right, is zero or is one, that's everything. But behind our computers, there is quantum physics, right? So that's something I guess is important to have in mind. So, for example, the funny thing is that in order to represent 0 and 1, you don't really need a transistor. I mean, transistors are good because we are able to synthesize, like to have a huge amount of transistors in a very little place. So that's why we can make computers so small, like my laptop here or your mobile phone, right? That's the advantages of using transistors. They can be compressed in very little places, and you can do computation with that. But the first computers were not made out of transistors, right? For example, you have here. I'm not sure if this is the first computer or not. I mean, one of the first, right? In a lot of like 50 years ago, or something like that. But they were. It was made out of some mechanical system that I'm not going to explain in detail, but the idea is that the 0 and 1 are encoded in another type of physical system that has nothing to do with transistor or electrical signals. And here is just some mechanical tubes doing different movement, and that's how they encoded 0 and 1 in this big machine that was capable of doing very much almost anything compared to what we can do now with our computers. So the idea is that we can use any physical system that we can imagine of to try and represent this 0 and 1 state that we use for computing. So what could happen is we try to represent this 0 and 1 state using quantum states, right? That's the approach of quantum computing. So let's move into that. So the quantum bit, also called qubit, as I have already said a few times, uh, is just take any quantum physical system, right? For example, here you have the spin. That's a physical system that we were describing the other day a little. We were using. So if you take the spin system, you have a bidimensional Hilbert space. So you can say that the up state can be your 0 state, and the down state can be your 1 state, and try to encode your 0 and 1 using this up and down state of the spin of your particle. It could be an example of how to make a qubit, right? But it's not necessary, strictly necessary to have just two levels, for example, and in here I know this picture might be a little confusing, but this is the way we represent energy levels of an atom. Like in an atom, you have electrons, right? An electron can be in different energy levels. Let's say yes. So this is the way to represent, and for example, this is the name of the first level, or like in the ground state level. But you don't really need to understand why the name is like that for sure. So you have uh, here you have one level. I mean, truly you have more levels than that. Depends on the physical conditions of your city. But just let's say you have here one level, here another level, another one, another one. I mean, you have more than two levels here. But anyway, you can try to if you have a quantum system with more than two levels. Or I mean, when I say levels, I mean also quantum states, right? I mean here because when we talk about energy levels in an atom, I mean each energy level represents a quantum state of the system, right? I hope that's clear enough. Sorry if sometimes I don't explain everything. But so if you have more than two levels, you can choose. Like like for example, they say, okay, for my Qubit system, I have a lot of levels. I will choose this one and this one. All right. And how to do that is not easy in this example, but it's possible, right? In fact, in the last day that will be this Friday, right, for this course, I will be discussing a little more about this exactly exactly this kind of implementation of a qubit. So we'll see that on more detail. So how do we write down uh, the state of a qubit? So we have already seen that a lot of in this introductory course since we were working with vectors. So let's say you have a Hilbert space made of two states, 0 and 1, and this 0 and 1 can either be the up and down state of the spin, or it can be any any energy level, the S and a half level, or these are energy levels. I mean, you just work with 0 and 1. I mean, and you don't really care I mean, when you are writing down equations like in doing quantum circuits or algorithms, you don't worry yourself with the physical implementation of the qubit. You just work with 0 and 1, like your 0 and 1 in the binary code. You don't worry about this. If in the classical bit, you don't really think about how it is made. If I mean, now we use transistor, but that's not important for the computation as long as we have the 0 and 1 states, right? So this 0 and 1 represents any quantum physical state that we will use, and that would be enough for us for doing the quantum computing calculation in terms of quantum circuits and all that. So this general linear combination that we have already seen. And remember that the other day we were discussing that in order to represent a quantum physical state, it must be normalized. And this is the normalization condition. Yeah, I mean, for to have a norm equals to one, you need to, this equality must be true. So, what's the interesting part in the quantum bit? Because there is a really big difference between this quantum bit and the classical bit. So the big difference is that in quantum physics you have quantum superposition, right? And this is just having a linear combination of two states. So when you have a linear combination of different states, you have a certain probability of being in 0 or in 1. So yeah, so quantum superposition. And when talking about quantum superposition, I don't know is whether it is easy to see or not, but you have an infinitive infinity amount of possible states, right? Because there is or there are infinite numbers that you can choose that satisfy this property. In a sense, you can have one point, you can have the number, but you can there are infinite numbers between this number and this number, right? So that's basically why I say there is an infinite amount of possible states given by the linear combination of 0 and 1. So while in the classical bit you just have two states that are 0 and 1, in quantum computing with the using qubits, we have two states for sure that are 0 and 1, but all the possible combination of 0 and 1. And that's is the interesting property of the qubit, and we can and the idea of quantum algorithms and everything is to try to use this special property of quantum system in order to improve computations, right? So there are out there are a lot of different ways of implementing qubits. And this is something that is still on development. I mean, each of this type of qubits is in development, and there are more type of qubits in development in the sense that we are in a point of quantum computing where things are good, but they still need a huge amount of improvement in order to have useful computers. So there is a lot of research on improving the qubits that already exist. Yeah, and try to find. I mean, if anyone find a new way to implement qubits that is better than the other ways, so that would be great, right? So there is a lot of research going on and try to find the best way to implement a qubit in order to create bigger quantum computers that are able to do better calculations. So, for example, we have superconducting qubits. The the leader in this case is IBM. I mean, they have a really good amount. I believe they said they were going to release a quantum computer which has like 400 qubits or something like that. I'm not totally sure, but I guess they said that, so that's good enough. For I mean, for 400 qubits, it's a really low amount of qubits if you compare to classical computers in the sense that the amount of bits in classical computers and also in quantum computing there are some problems that I will talk in the next slide that make us need more qubits in order to do proper calculation. So superconducting qubits, I mean, I'm not going to explain a lot about superconducting qubits. Also, trap ion qubits. Mm, this is just using a trap ion and try to use. I mean, this is the implementation that we are going to discuss in more in detail the next Friday for the last day of this course. So we will see more details on that lecture. Also, we have neutral atom qubits. In here, you just have where I have taken the image from, right? In case you may want to take a look or anything. We also have photonic qubits that are using light, and taking account that for each of these qubits, I mean, for example, superconducting qubits or yeah, photonic qubits, there are different types of superconducting qubits, and there are different types of photonic qubits. So in here, my idea was just to give you an idea that there is a lot of different ways to implement qubits, but at the end, the point is to have a quantum system that can be either in 0 or 1, right? That's the idea. There is a lot of research and development that needs to be done in this matter. So And why? Why do we worry so much about type of qubits, and why do we need so much research? And as I have said, so working with quantum system is extremely difficult because quantum properties appears like in very special cases when you have maybe you are working with very low temperatures, and that means like near 0 Kelvin. I mean, the absolute zero temperature. Sometimes you need to work with that temperature. Also, sometimes when you, for example, with trap ions, you need to trap an ion, and that's crazy because, for example, in the air that we breathe, right, in order to stay alive, there are oxygen molecules and other type of things that are in the air that are much bigger than just an ion. So trying to trap an ion and manipulate the ion in order to get a proper calculation is quite a challenge. And for every type of qubit that I have shown here, yeah, other type of qubit that I haven't shown, but there are more type of qubit that I have that the ones that are here. There are it's extremely complicated to manipulate and control and do proper calculation with qubits since quantum systems are really difficult to control, right? So there is something called the coherence. That is just you lost the information. Let's say you lost the information while doing computation. Stability of your qubits, scalability. Scalability is related to just you need a lot of qubits, right, in order to have a useful computer that we do not really. I mean, there is not a quantum computer that has all the power of quantum computing, right? In the sense that it cannot replace a classical computer. It cannot, for example, it cannot yet break cryptography, normal cryptography that we use in our classical computers. So there is not yet such a powerful quantum computing due to this scalability fact that it's difficult to have whether you have a qubit or right, but just one qubit is like you cannot do much about that because you need a lot of qubits in order to encode information. So it's important to be able to find a way to make your system grow, the amount of qubits properly. Right, connectivity, because sometimes uh, you can have 500 qubits, let's say, for example, but are they all the qubits connected? Like you have them I mean, is your implementation good enough in order that you can every qubit in your system can talk to each other? So for some system, for example, superconducting qubits in the IBM machine, I mean IBM quantum computing, they are not connected in this like the connectivity is not one to everyone. There are just some kind of mapping where you can see, okay, this qubit is connected to this other qubit and to this other qubit. So in order to do proper computation, you should try to just do operation using qubits that are near, right? They are connected, right? Measurement is also sometimes complicated. There is a lot of error in quantum computation, and that's why error correction is quite a big branch of quantum computing, and it's one of the main reasons that quantum computers need so many qubits in order to do proper calculation. Also, well, this has to do more with developing algorithms, but we need to uh, give a little work to develop software and algorithms since quantum computing works a little differently since you have more this quantum superposition thing. So in order to do proper calculation and improve the the classical algorithms, we need development in trying to find new ways to use these quantum properties. The physical implementation is difficult, I have already said. For sure, normally every kind of Qubit is really expensive, like in order to find the facilities and materials and anything you need in order to do the implementation of your qubit is very expensive. So there are a lot of problems to solve, but there is a lot of research ongoing. So let's hope for the future, right? uh, and the blockchain, right? So we have talked about the quantum bit, that is just a quantum system, and we encode 0 and 1 in the states. So there is another way of writing, because this is the linear combination that we have seen already a few times. There is another way of writing the very same linear combination, I mean, just this guy, but using another type of coordinates, if you want, because now you have here alpha and beta that can be any complex number. For example, instead of using alpha and beta, we could use these angles, right? These angles, and we write down the qubit in this way. So let's analyze this a little. So basically, you have here your cosinus, that is the fair coefficient, and this exponential, this complex exponential, because we have here the I there, the phi, and this angle, this will be the corresponding complex angle of this complex number. So this is usually called the phase. The phase. I don't know if I said this in the first lecture about complex number, but this angle in the exponential of with the imaginary unit is usually called the phase. So and we have here the sinus. So for example, you can check. It's easy to check that every time you write a state in this way, the norm equals to 1. I mean, this condition is satisfied because if you will get the norm of this guy will be just well, I'm writing in red. Sorry for that. uh, remember that when doing this, we have to complex conjugate this guy, because remember that the norm was just the square root of the scalar product of the same vector with the same vector, right? So yeah, and remember that the scalar product that we are using in quantum mechanics, in this case, is similar to the scalar product in Euclidean space, like the vector space that we use in high school, but doing the complex conjugate to the fixed coordinate. So that's why the complex conjugate. So at the end here, you get uh, this square, and also the complex conjugate, you get here a minus sign, and this cancels with this guy. So at the end, you get this, and using basic trigonometry stuff, this is 1, right? This. So that's so it doesn't matter the angle; it can be any angle. This will, I mean, any angle, any real angle for sure. I mean, because angles can also be complex number, but in this case, that's not what we want. So any angles in these intervals, we will have a physical state in the sense that it's going to be normalized, properly normalized. Right. Apart from that, we have here the imaginary, I mean, because, for example, this is going to be a real number, always, real number. And this is all, well, not always, but it will be complex number. It is going to be always a complex number because real numbers are a part of complex number also. So anyway, in order to understand this better, I have a few examples. But before going into the examples, let's try to understand this. So why is this interesting? I mean, why, and also why this is called. I mean, this is a Bloch sphere here. So, in order to introduce the Bloch sphere, first we have to do this change of coordinates that we have done. We have just done. So why is this change of coordinates interesting, and how is it is related to the Bloch sphere? So, as I have written here, the Bloch sphere in the okay. The Bloch sphere is just a sphere, right? With the radius of the sphere equals one. If you have your sphere, right? So the radius of your square will be one. I'm not that good at drawing. And if you are familiar with spherical coordinates, this might be easier to understand. And if not, anyway, I will try to detail a little. But you have uh, the radius equal one, I have said. So any vector in the surface of the sphere, is going to have norm equals to one, right? Because if the sphere have radius one in the space, let's say, that means that any vector, any arrow that you can draw, like when we talk about it, because remember that at the end vectors represent different things, but when you use the matrix representation, at the end you have vectors that, and you can draw them like arrows in your space. So you have module one arrow that's have to do with the radius one of the block sphere, and the freedom you have in the sphere is that okay, you are on the surface because the vector must be normalized, but you can move in the surface to any point. And in order to move in that surface, you use these angles. And it's the theta angle and the phi angle that are, and this angle are these that we have already seen. So this theta angle move, and I don't know if you can see it properly. Let's try to. So this angle move into, you see this axis here, right? The angle is between the vector and this axis. And y is between 0 and pi, because pi is, just in case you are not familiar with using this kind of angles, pi is just equals to 180 degrees. And this is also, uh, yeah, 360 degrees. So because theta goes from 0, this will be theta equals 0 when you have a vector in this in the axis pointing up, and it moves all the way down to here, right? I mean, when you have the vector in the same axis, but down, and that's how you move using theta, right? Just yeah, this, and this is this the range of the movement, if you want, in the Hilbert space is 180 degrees or pi. That way is more common to use pi or in everything. This yeah. So that will be theta. I want to erase it. And phi is just the angle between the projection, right? This, I mean, if you have the vector here, this will be the projection over the horizontal plane, right? That will be the projection. Yes, so it's the angle between this axis and this part of the axis, right? And the projection. So is this angle. And in order to move or to all the states, you will you can do the whole circle, and there will be a 2 pi angle. So I hope now you understand a little more how this works with the angles, and also what I have already said, or you can read it's written here. Every point in the surface of your Bloch sphere represents a physical state of your quantum system, right? For example, take theta equals 0. Yeah, it doesn't matter. Take theta equals 0. In that case, it will be cosine of 0, and that is 1, right? So it will be 0. And the sinus of 0 is 0. So when theta equals 0, it doesn't matter. I mean, the angle phi can be anything, but if theta equals 0, phi is the 0 state, right? And that's why, I mean, and that's this point in the sphere, this point that is up into the very top of the sphere is the 0 state, and that's why here you have this 0 indicating that that point relates to the 0 state. For example, if you now take theta equals pi, and you can see that it's going to be 1. But anyway, if you do the cosine of pi, and it will be the cosine of pi and a half, since this 2.5. So this will be 0 and 1. I mean, uh, like the cosine of pi and a half is, I mean, pi over 2 is just 0, and the sinus of pi over 2, the sinus is just 1. So you get this. And it will be this point in the first, and it will have theta equals pi, this point in the bottom. And now you can see that, because remember that we are also working with orthogonal bases. States that are orthogonal in the Hilbert space are represented in the Bloch sphere are points that are how to say in the same axis, but in the contrary the contrary part. I mean, if your state is in the top here, the orthogonal state is going to be down here. If you have another state here that we are now going to see, your orthogonal state will be this one, this point here. And also here, if you have one state here, the orthogonal will be this point here, and that will be for every point in the sphere. So that's what I was trying to say. Right. So let's see some more difficult examples. Take t theta equals to 90 degrees, or pi over 2. If you do that, you will get here pi over 4. And pi over 4 is just the cosinus of 45 degrees, and just the half of 90 degrees. And that's just 1 over the square root of 2. So that's why you get this and this. And also this plus minus comes out of the phi angle. In here, I have draw the two vectors that are the +1 and the -1, but here I have just written the phi equals 0, and that corresponds to the x mass angle. Since phi equals 0, it will be like this exponential will be just 1. But if you have like this, right, this will be the phi angle. In this case, will be pi, right, or 80, no, 80, I'm sorry, 180 degrees. So this complex number equals -1. right? So that's why you get the minus here when you have phi equals to phi. This angle equals to a pi, right? So and this vector is the one that we were discussing the other day when doing this Ster-Gerland experiment and the Pauli matrices, right? This is that vector, right? We could also go to this other axis. So in this case, we also have theta equals to pi over 2, right? And we are in this direction. But in this case, there is the phase, and with the phase, I mean the phi angle is different because for the plus, we have phi equals to pi over 2, and that's because remember this is for the complex number. Remember the first day. This will be just the the imaginary unit, right? And also in here we have this the complex number, and this is minus the unitary unit, the imaginary unit. So that's why you get here the plus, minus, and the imaginary unit. So using Bloch-Feld is like a really good way to use to represent physical states and to visualize operations. So that's why I wanted to give some time to this. Since we are running a little late and still a few stuff to discuss, I will go very fast to some things that I feel that are not that important, are not so important. But anyway, so density matrix. The density matrix is just a matrix, right? Just a matrix, yeah, right, basically, that we use to describe a quantum system. So in here we find something a little more advanced that are mixed state, but try to forget about that at this moment. So if we have a pure state, and a pure state is any state in your Hilbert space, any state. It can be just zero, it can be just either one, or it can be any general linear combination or zero or one, or if you are another. I mean, this is not something special for the qubit. This is something that you can use for any quantum system. So it's just any state vector of your Hilbert space, right? That's what we call a pure state. So the density matrix will be just the matrix that you get out of doing this calculation. So that's quite a straightforward definition. So a mixed state is something a little more difficult, but it's just a linear combination of pure state density matrices. I mean, if you have, for example, rho 1 and rho 2 that are different density matrix out of different states, you can have a mixed state that is, for example, 1/2 rho 1 plus 1/2 rho 2. And that will be a mixed state. It's important that this coefficient, and in this case is 1/2 and 1/2, they must sum up to 1 because that's basically the probability to be in one state or another state, similarly to the probability that we work, like when we work with the vector state, and the coefficient is related to the probability. When here is the same, but these are density metrics, not vector. So density metrics satisfies important properties that they are just there. So I'm not going to discuss more. So just to take this to an example here. Mm, let's say you have the usual linear combination that we use to describe any state of the Hilbert space, and we calculate the density matrix of this state. So just do this calculation, and you will get that the density matrix is can be written in this way using the 0 and 1 basis, because remember that every time we write a matrix, we are using some basis, right? Uh, and mixed state. For example, let's say a mixed state that have zero, and this probability of being in the zero state have this probability or of being in the one state. So if it will be this matrix here. And the funny thing is that these states, the states that are being described by this matrix and the other matrix has they have the same probability or to be in zero or one, because the probability to be in zero here is just the alpha square, and the probability to be in the one state is this beta square number. So in here, in this mixed state, the probability is the same, but the state is different. So this is related to the coherence of your qubit, in the sense that you are losing information about the phase. Mm. The phase in a quantum state is an important detail. Like, for example, here, remember, the only difference between these states, and these states are very much different, is the phase here, the angle field, right? Is the only difference because the theta angle is the same. So in the phase, there is a lot of information about the quantum state. So when you have a mixed state, it's like having a pure state, but you have less information because in some way you somehow you have lost that information. So that's something I wanted to say. Oh, yeah. This is a little more difficult. I thought I would have more time to explain this in more detail, but basically, this is just take it as complementary, since this something more, this has, I would say, details. So here you have a calculation that you can try to see at your own. I mean, with the things we have already seen in the quantum mechanics basis and the Dirac notation lecture, you should be able to understand this. But if you have any problem, ask me anything on the Discord server or whatever. You can always do that. But the only important idea here is that using the density matrix of a system, right, you can calculate the expected value. Remember that expected value was the way of getting some experimental information, in the sense that you have to repeat. It's like a time average, right? It's some kind of time average, and we discussed this a little in the last day lecture, I think. So you can calculate the expected value of any operator, of any linear operator, by doing this computation. Here you have the corresponding density matrix to the state here, and the linear operator, and this is the trace of the matrix. Because at the end, uh, this uh, this density matrix is going to be a matrix. This linear operator can be written as a matrix. So at the end here, you are going to have a matrix. You're going to be the multiplication of these two matrices. So the trace of that matrix that you get out of multiplying these two can give you the expected value. And using that, if you remember how to compute the probability of being in a certain state, and these are, remember, AM values and all that. So you can compute the probability using this density matrix and also the trace of a state. So that's basically the important thing here, that in order to calculate the probability or calculate expected values of any operator, you can use the density matrix and the trace of a matrix, right? That's what I wanted to say. And now here, this is something more important, so that's why I wanted to come here faster. So because the density matrix is something important, it's more related to quantum information stuff, and it's important to understand density matrix, but it's not multi-qubit system is more fundamental for us in this introductory course for sure. So multi-qubit system. So as I have highlight at the beginning, we need more than one qubit and more than two qubits for sure to do proper computation. So how do we work when we have more than one quantum system? And that is something that I haven't really talked about. but it's something important. I mean, in here, I'm just going to do that for the sample of a qubit system, but this is something general than you work when you work with Hilbert spaces and you have more than one Hilbert space. It's something that you use, and it's always the same, I would say, more or less, depending on some mathematical details, but the idea is always the same. So if you have two qubits, let's say you have H1 and H2, and each of these Hilbert spaces are just a qubit, right? So in here, this is not strictly necessary, but uh, in order for making more clear, I have added the one just to make you know that I refer here to the first quantum system, and the two here in order to you know that I refer to the second quantum system. So this operation here, this strange multiplication symbol, is called tensor product. Tensor product. I'm not going to detail on the tensor product. I mean, it's not my point. But the only thing to tell you is that when you have more than one Hilbert space, and you want to work with that, you have to do the tensor product of your Hilbert spaces. At the end, what's the meaning of that? The meaning of that is that, for example, the tensor product, you just multiply each of these guys. I mean, you multiply 0 times 0, 0 times 1, and multiply, I mean, do this kind of multiplication. And this means in the this will be the tensor product of the vector 0 of your first Hilbert space and the vector 1 of the second Hilbert space. So in order to write this more like I would say in a more comfortable way, we understand that if we write this, this refers to the first quantum system, and this refers to the second quantum system, like the order, right? In how we write them is what we use in order to understand what we are referring. No, because I mean the more precise way of writing this will be this one, but it takes too much space right now. I mean now it may seem a little silly, but when you do big computation, it's I mean things get really messy. So this is something very usual. I mean everyone writes down the thing like that, like this. So you have the tensor product of two Hilbert spaces that are, and each Hilbert space is a qubit system. I mean, this is a two-dimensional system, right? And this is another two-dimensional system. At the end, you get a four-dimensional system because it's two times two, but you get four dimensions, right? And you get this new Hilbert space that is the tensor product of your these two Hilbert spaces here. And you work, I mean, it's exactly the same. It's just a Hilbert space, but now you have four states, right? I mean, you have it's a four-dimensional Hilbert space. Sometimes when you work with these things, you can rename the vector in the basis. Like, for example, take these guys and you can call them 0, 1, 2, and 3. You can do that. When you do that, you need to make very clear that this 0 and this one are a label for referring to this 0, 0 and to this 0, 1, because again they care about that we are these names are just names. I mean the important is the what they represent, because this 0 in this case, right, in this case represents a 0, 0 state of 2 qubits, because I'm using that name if I wanted to. But so that's why it's important to make every time you're working to make very clear what the notation and symbols that you're using to specify what exactly they are, because it can be a little confusing sometimes. right? So when you how do you write operators in order to apply operators mm, to any multi-qubit system? So you do this like this. I mean, you also do the tensor product of operators. For example, here I will have letting a parenthesis, but you have an operator that that can be a that acts on your first qubit, and another operator that's the same, or any other operator. I mean, it can be they can be different operators. That's why I say a one, a two. I mean, I could have also called this B2 or whatever. I mean, they can be different operators. So, but if I write this in this way, I mean that the first operator is going to be acting on the first qubit, and the second operator is going to be acting on the second qubit. It is also usual to find this. I mean, and sometimes you don't, they don't even write this. I mean, if they sometimes they don't explain that much, in the sense that since it's something much people think it's easy to understand how they should be, they don't write that much. But if you have this um, operation here, it's the same as writing this, because this operator is acting on the first qubit, but not in the second qubit. So it's the same as doing this tensor product when you have your operator, and this is the identity in the second qubit space, right? That's just something that I believe that can be a little confusing. And this is just the last slide of today. Uh, so this is just another example. I mean, this is exactly the same I have just said, but with a general example of n qubits. So if you have n qubits, and that means you have n Hilbert spaces, each of them representing a qubit. You just have you just have to add more Hilbert spaces to the tensor product here. I mean, you go h1 times h2 times h3 times until you finish, right? With your with all the Hilbert spaces that you are working with. So this means that if you have a qubit, let's say 0, 0, 1, 0, 1, sorry, 0, 2, 1, for example. I don't know, and more and more and more. You have more and more until uh, you get, I don't know, 0 again, for example. I mean, I'm just using a random number. I mean, it's the same, but just adding more. Adding more, you can add the amount of qubits you want in your theoretical calculation. And this could also be denoted at 0, 0, 1, for example, 0. And this following what I have written here, 0, 0, 1, 0, 0, 0, 1, 0, right? So the dimension of the system will be 2 to the power of m, right? Because for each multiplication of the Hilbert space, we are doing 2 times 2 times 2, since each of the system is bidimensional. Also the same as I have said before, if you have operators, and you can have a 1 times, let's say, or another operator B2, another operator C3, times another operator AN, whatever. So each of these operators are going to be acting on the corresponding qubit, right? As the same as when we have two qubits. And also here, if you may just write one operator, and in order to do that, in some way, you must know into which qubit the operator is acting, right? For example, if it is acting on the first qubit, it means that for the rest of the qubits that you have in the system, um, is going to be the identity, right? So, um, so that would be, yeah, I think that would be everything. So Here are some reference. I feel like the screen is frozen. I don't know why, but anyway, I have just finished, so good enough. Yeah. So here, yeah. Now, now it's okay. Yeah, the screen was frozen. So see you the next lecture.